Hello viewers, welcome to my channel KK Concepts of Electrical Engineering.
Now, self-inductance of Toriod. Now, I'm considering a toroid. This is nothing but a tube. Now, the current flowing through the toroid is I, and the radius is R, having mu is the permeability, and n is the number of turns. Now, if you take this cross section, then it looks like a circle having a radius small r. Now, considering at a distance r. From the previous video, we know the flux density of a toroid is B equals to mu Ni divided by 2 pi r. The link is given in the description. Please go through it. Flux linkage for this is number of turns into flux. We know that the flux is given by area multiplied by the flux density. B is given by A mu Ni by 2 pi r. Flux linkage to the coil is given by, that is Ni, that N into phi is equals to Na mu N square A mu I by 2 pi r. The self-inductance from the definition L equals to N phi by I, then N square A mu I divided by 2 pi r multiplied by I, and I gets cancelled, then N square A mu divided by 2 pi r in henries, where A is the area. A equals to in this circle, so it is pi r square. Now substitute that, then N square pi r square mu divided by 2 pi capital R. Pi gets cancelled. Self-inductance of the triode is given by L equals to N square r square mu not mu r divided by 2r, where r is the radius of the triode in Henry. Inductance of a coaxial cable. Let us consider a coaxial cable having inner cable carries a current positive I, and outer cable carries a current of negative I, having the radiuses A. From here to here it is, let it be B, and from here to here it is, let it be C. Considering the radius R inside the outer cable, let this be R. The length of the cable is, let this be a D, which is assumed is along with the z-axis. The magnetic flux contained between the conductor lengths D of the cable is equal to flux crossing any radial plane. Now, from the previous video, field intensity in between the inner outer conductor of the cable, B is greater than, R is greater than A, H equals to I by 2 pi r. Link is given in the description. Please go through it. B equals to mu H, that equals to mu I divided by 2 pi r is the flux density in between the inner conductor and the outer conductor, that is in this space. Now, the flux phi is given by B dot ds, and this flux remains in entire cable in between the inner conductor and the outer conductor along the length of the cable z. So integral 0 to d, since it stays along the length of the cable and between A and B, so it stays in between A and B, then mu I by 2 pi r dr and dz. Then this in magnitude it will be mu I by 2 pi. If you do along the z, that is z 0 to d, along r, that is 1 by r, so log to the base e along r A to B. Substitute this will be mu I by 2 pi Z. So D minus Z multiplied by log B minus log A to the base is. Then this is equals to mu I divided by 2 pi of D of log B by A to the base E, which equals to mu I D by 2 pi log B by A to the base E is our flux. Now we got the flux of the coaxial cable. Now inductance or self-inductance L is given by N phi by I, where N is the number of turns. In a coaxial cable, number of turns is equals to 1 and phi we know I is the current. Now substitute these things, then you are going to get mu I d by 2 pi log B by A to the base E is the N phi divided by I. Now I gets cancelled, then you are going to get mu D by 2 pi log B by A to the base E is our inductance L in Henry. This is the inductance of the cable to the entire length D. Inductance for unit length, then L equals to mu unit length, so D is equals to 1 divided by 2 pi log B by A to the base E in Henry.
If you have any suggestions and queries, please mention in the comments. If you like this video, please like, share and subscribe. Thank you for watching the video. Please stay tuned for more videos.